Okay, number 6. A gas has a volume of 650 milliliters at negative 35 degrees Celsius. What volume of the gas? Okay, so I noticed right away that the only thing that's being talked about here is volumes and temperatures, right? Volumes and temperatures. There's everything else is keeping the same. So I could use PV equals nRT, but there's an easier way to do it. Like I just think to myself, what is the law that covers the relationship between volume and temperature? So V and T. Charles's law. So V1 over T1 equals V2 over T2. Because again, it's the only thing we're interested in here is the relationship between the volume and the temperature. So the gas has a volume of 650 milliliters. So I'm gonna keep my volume in milliliters because it's asking for a final answer in milliliters. But I could change it if I wanted to. So anyways, I'll just keep it. So 650 all over negative 35 plus 273, because I gotta have it in Kelvin, equals V2 all over 40 plus 273. And so now I just got to go at 650 times, looks like 313. That's this right there. Add it together. Divided by, so negative 35 plus 273. This one I'm just going to double check on the calculator. Looks like 238. 238. And then it will equal V2. And now it's just calculator time. 650 times 313 divided by 238. And I get a final volume of 854.8. So 854.8. And that's in milliliters. Again, if for whatever reason I had to convert it to liters, remember there's 1,000 milliliters in a liter, so this would just simply be 0.8548 liters. It's the same answer, right? It's the same number. Next one. A gas in a piston occupies 300 milliliters at 730 millimeters of mercury. If the piston is moved to change the volume to 2 liters and the pressure drops and the temperature is 40, what was the original temperature? Okay, so it looks like we have volumes, pressures, and temperatures, but no moles or like anything like that. So this is going to be the combined gas law. So we're looking at P1 V1 over T1 equals P2 V2 all over T2. And it's asking for the original temperature, right? So it's actually asking for this. So what I'm going to do is I'm just going to solve it for T1 right away using algebra, just because it's going to save me a step later on. So in order to solve for T1, I've got to multiply both sides by T1 to get it to the numerator. So it's going to be P1 V1 equals P2 V2 T1 all over T2, right? Because all I did, again, brought it over there. And then I got T1 alone, so I'm going to multiply both sides by T2 and then divide by P2 V2. So again, I'm going to combine a couple steps because I'm already running out of space, I can tell. So it's P1 V1 T2 all over P2 V2. That's going to equal T1. And now I can just solve. P1 was 730. V1 was 0.3. I'm going to do this in liters. 0.3. The T2 is the final temperature, so that's going to be the 40 plus 273. The final pressure is 700, and the final volume was 2. And this should all be equal to T1. So now it's just calculator time. 730 times 0.3 times, looks like 313 divided by 700 times 2. And I get 48.96 degrees Kelvin, which is pretty darn cold, but it is what it is. I'm just kind of double checking my numbers here. Yep, it is what it is. Okay, so 48.96 degrees Kelvin. Yes. All right, moving on to the next one. How many liters does 50 grams of O2 gas occupy at one point? Okay. So here we notice that we're given grams of O2. So the PV equals nRT. This right here has to be in moles, right? The N has to be in moles, not grams. So the first thing we got to do is convert 50 grams of O2 into moles. That's our first step. So let's just do that real quick. 50 grams of O2. Remember, using the periodic table, each mole of O2 is 16 grams. So O2 is 32 grams for a single mole of O2. So 50 divided by 32, 1.56. So 1.56, that's rounded. So that's how many moles of O2. Okay, now we can get started here. We're trying to figure out how many liters it occupies. So that is a volume. So volume is equal to nRT all over P. So volume is equal to 1.56. Now I got to use the correct R value. I have to use the R value that corresponds to ATMs, and that's 0.0821. The temperature is 15 plus 273, and all of that is over the pressure, which is 1.5 ATMs. So 1.56 times 0.0821 times, it's like 288 divided by 1.5, and I get 24.6. 24.6 liters. All right. Okay, there's the video for number 9 and 10, the last two on the practice test. N2, inside a closed 450 milliliter flask is kept at a pressure of 3.5 ATMs and a temperature of 375 Kelvin. How many moles of N2 are in the flask, and how many grams of N2? So this is similar to 8 in the sense that we have to at one point do a conversion from grams to moles, or in this case from moles to grams. Let's get started. PV equals nRT. So we're trying to figure out the number of moles, so let's just solve for N. N is going to equal PV all over RT. And now we can I think we're just ready to go. We're just ready to calculate. So N is equal to 3.5, 0.450. That's 450 milliliters into liters, right? Just divide by 1,000. The R value, I need the R value that corresponds to ATMs, and again, that's 0.0821. And the temperature in this case is already in Kelvin, so I'm not going to convert it. That would just make a mess of this. So it's already in Kelvin, see? And now we just calculate. So 3.5 times 0.45 divided by 0.0821 times 375. And I get 0.051 moles of N2. Now we got to convert that into grams of N2. And do I literally have to get up and find it? Okay, I got to grab a periodic table real quick. All right. I believe N was 14, but I thought it was 14.01 or something, but I don't want to guess and have to redo this video. 14.01. So, we have 0.051 moles of N2. 1 mole of N2 is since a mole of just single N is 14.01, N2 is going to be 28.02 because you're doubling it, right? 28.02 grams. Again, because we have 2 nitrogens, not just 1. So 0.051, 1 times 28.02, 1.43. We get 1.43 grams of N2 gas. All right, last one. A gas originally at 225 degrees Kelvin has its pressure tripled while the mole of gas and the volume remain constant. What is the new temperature of the gas? Okay, this is similar to one of the earlier ones where, if I remember, so this is similar to number 4. and that you're sort of keeping a couple of the variables constant, and you're trying to figure out what is the effect of changing one on changing the other. So let's just start with PV equals nRT. It says that the moles of gas and the volume are going to remain constant. So we're not changing V and N. R is always a constant, so that's not changing. So this is really similar to the previous problem. We're just saying, okay, what if you triple, so we're going to say 3 times. If you triple the pressure, what's the effect on the temperature? Now, in the previous one, we didn't have it. We weren't just a simple tripling. We had to go from 5 to 7, which is like a factor of 1.4. That was a little harder, right? You had to figure out what factor is 7 from 5. Here it's even easier because they just straight up tell you you're tripling. If you triple P and change nothing else, doesn't that just triple T? And if you said yes, you're smart and you win a prize. So the original temperature was 225, and we are tripling it, and that is going to be 675 degrees Kelvin. That is literally it. Okay.